In this session, we will be talking about probability distributions and the probability densities, density functions, etc. So, as an agenda of this session, we will first get started with what are random variables, what are the different types of random variables like discrete random variable or continuous random variable. So, once we understand the random variables, then we will bring in the probability distributions. Distribution functions. What do we really mean by a probability distribution? And taking a few examples relating to the probability distribution. So we will spend first some time with respect to discrete distributions. Then we will move to continuous random variables. How do we differentiate the continuous random variables from the discrete random variables? What are the key differences that are existing between them? And how do we really work with continuous random variables? Then we will be introducing the probability density functions. And again, we'll take a few examples to work out with the probability density functions. So up to here, it would be more of univariate, taking one single variable at a time. But from here onwards, here we would be focusing on taking two variables together. So we would also be interested in exploring the relationships between the variables. So that is what we would be talking of in bivariate distributions. And then multivariate distributions, the same bivariate extended to multiple variables. So we will be taking an example regarding the multivariate distributions. Then marginal distributions, how they are derived from using the bivariate distributions. What do we mean by the marginal distributions? Again, we will spend some time regarding that. And we would also be interested in looking at conditional distributions, right? X given Y kind of distributions. So that's one more area. And towards the end, we would be looking at independent events and how the distributions are going to come up with respect to the independent event. So let's get started with all these things. So initially, random variable. If S is a sample space, all right, and so X is a real valued function defined over the elements of S. So in short, if I'm talking about a sample space when I'm throwing a dice, the sample space when I'm throwing a die is 1, 2, 3, 4, 5, 6. Now, I'm talking about X as a random variable. So X, I can simply say a number 4 coming up. That is what, or probably whatever is the outcome of the dice. The outcome of the dice is typically a random variable because the outcome, it could be 1, it could be 2, it could be 3, any one of these 6. Similarly, when I'm throwing 2 dice, I can say the sum of the values on the 2 dice is a random variable. So anything which any outcome or a set of outcomes that are coming out of a sample space, I am trying to observe one specific function over the elements of this sample space. Then X is called a random variable. So let's say I'm talking about tossing a coin 3 times, right? Tossing a coin 3 times. Now X, I'm calling it as getting heads, number of heads that I get. So there is a possibility that I will get 0 heads. There is a possibility that I will get 1 head, 2 heads, 3 heads. So X, when I am saying number of heads that are coming up when I am tossing a coin 3 times, it could be it can take a value 0, it can take a value 1, 2, 3. So that is what we are simply denoting when we are calling it as a random variable, because that outcome could be very much random. So the total coming up when 2 dice are rolled, in general, we see that the random variable, whenever we are using the word random variable, we are denoting it with a capital letter like X, and the value that is taken by the random variable, we will generally denote by a lowercase letter x. Okay, let's look at a couple of examples to get a clarity. 2 socks are selected at random and removed in succession from a drawer containing 5 brown socks. Okay, there are 5 brown socks and 3 green socks. So I am taking 2 of them at random. List the elements of the sample space. So what are the elements of the sample space here? I'm picking 2. So there could be 2 brown ones only that could be picked. There could be 1 brown and 1 green one that could be picked. Or I could have picked 1 green first and then a brown. Or I could have picked both the green. So this is my sample space. Right? These are the various possibilities. List the elements of the sample space. Then what is that we are looking at? The corresponding probabilities. Okay. What is the probability that I will pick both of them as brown? So totally there are 8 socks. So the number of picking 2 from 8 can be done in 8C2 ways. But in the numerator, I am picking 2 from 5 brown socks. So 5C2 ways. So it becomes 10 by 8C2 is 28. So this is 10 by 28. Then what about first one being brown and the second one being green? The first one being brown, I am picking it in 5 by 8 ways. The second one being green, now there are only 7 things that are left. Out of these 7, 3 greens are still there, so 3 by 7, making it 15 by 56. First one green can be picked in 3 by 8. What is the probability picking a first green? 3 by 8. Second, there are still 5 more browns, so 5 by 7, making it again 15 by 56. And finally, both greens, 3C2 divided by 28, which makes it 3 by 28. So these are the typical possibility. Okay, corresponding probabilities. Corresponding values, W of the random variable. So now I am looking at a random variable W. W is the number of brown socks selected. So W as a random variable is the number of brown socks selected. So it could be 0 brown socks, it could be 1 brown sock, or it could be 2 brown socks. So I want to really find out what is the probability that is associated with picking 2 brown socks, 1 brown sock, 0 brown sock. So corresponding to 0 brown socks, it is both of them being green, which is 3 by 28. 1 brown sock, it could be this one or this one, making it 30 by 56 or 15 by 28. And probability of picking both of them as the brown socks is 10 by 28. So these are typically the probability values associated with this random variable. So the random variable W, which is the number of brown socks that are selected, it could be either 0 with a probability of 3 by 28, 1 with a probability of 15 by 28, and 2 with a probability of 10 by 28. So these are the different values that could be taken by this specific random variable. Okay, let me take one more example to get an understanding of the random variables. A balance coin is tossed 4 times. List the elements of the sample space. This is a known one, right? So I'll go with HHH. So I'll have T, HHH, T. Then we are going with HH, TH, HH, TT. Now we are increasing this thing. So there are already 16 possibilities that are going to come, which we know. List the elements of the sample space that we presume to be equally likely and corresponding values x of the random variable x, the total number of heads. Okay. So I require total number of heads. So x is a random variable which is taking total number of heads. So x can take any one of these possible values. X can be 0, 0 number of heads, 1 head, 2 heads, 3 heads, or there could be 4 heads altogether. What is the probability that I will get 0 heads? 0 heads is all 4 tails, which is 1 by 16. 1 head. The first one could be a head, second one could be a head, third one could be a head, or fourth one could be a head. So that's where we are talking about 4 by 16. 2 heads. The first and second, first and third, first and fourth. Second and third, second and fourth, third and fourth. There are 6 possible ways in which 2 heads can come, making the probability as 6 by 16. 3 heads, right? 1, 2, 3, 1, 2, 4. 1, 3, 4, 2, 3, 4. Only 4 possibilities are there, so making it 4 by 16. All 4 heads, 1 by 16. So this is a typical different set of values that could be taken by the random variable and their corresponding probabilities. Now this is how we define our random variables in general, right? Any particular if I'm doing a particular experiment some number of times, I'm observing one specific aspect like getting heads. I'm seeing how many times that particular aspect is coming up, what are the different values that could be taken by the random variable, and what is the typical probability that is associated with the random variable. So this is typically called a probability distribution, right? This kind of a table that I am making is called as the probability distribution associated with the random variable. There are various other ways of representing the distribution, but taking different possible values of the random variable along with their associated probabilities. That is what we are calling as the probability distribution of the random variable. Now in this random variable, we could have a discrete random variable whose range is finite. As you have seen here, when I am tossing a coin 4 times, I can get only 0, 1, 2, 3, 4 heads, nothing more than that. So only it's a finite set of values that my random variable can take, or even if it is infinite, it is countable. In that case, we call that kind of a random variable as a discrete random variable. Whereas coming to continuous random variable, the whole thing is defined over continuous sample spaces. The number of values that a random variable can take are literally infinite. So that's the one basic understanding that we need to have with random variables. Lots of probability related calculations works depend heavily on the understanding of the random variables itself. Once we got a basic hold on the random variables, then we will be moving on to our next topic, where we would spend some time in terms of understanding probability distribution. As I have just given you a basic hint, if x is a discrete random variable, that is what it was in our earlier cases, right? We talked about four 0 heads, 1 head, 2 heads, 3 heads, 4 heads. So it's a discrete random variable. The function f of x equal to p probability of x equal to x. Probability of x equal to 0 is 1 by 16. Probability of x equal to 1 head was 4 by 16. Probability of x equal to 2 heads was 6 by 16, and so on, right? So the function that I am giving for each x within the range of x is what we are calling as a probability distribution for that particular value. So in some cases, instead of displaying the probabilities associated with each of the random variables like this is where I am displaying the probabilities established associated with each of the random variables, because I am saying random variable x takes on 0, 1, 2, 3, 4. I'm also saying the probability of x equal to x is 1 by 16, 4 by 16, 6 by 16, 4 by 16, and 1 by 16. This is the way we are expressing it in form of a table. In some cases, we try to express these probabilities in terms of functions. So when I am establishing the probabilities in terms of functions, that is what we are calling it as a probability distribution function. So if at all I am looking at any function I am looking at, if it has to be a probability distribution function, a few things. The values of f of x should be greater than or equal to 0. So which means each of the probabilities should not be should be non-negative. They should be greater than or equal to 0, and summation of all those probabilities should be 1. So if you look at this, 1 by 16, 4 by 16, so on, the summation 1 plus 4, 5 plus 16, 11 plus 4, 15 plus 1, 16 by 16 working out to 1. So only if these two, which means individual probabilities should be a non-negative, sum of all the probabilities across all the possible values of the random variable should be equal to 1. So then only a particular function which we are choosing could be a probability distribution function. Let's look at a couple of examples to understand that. Find a formula for probability distribution of total number of heads in 4 successive tosses, right? This is the same example. For 0, I want it as 1 by 16. For 1, I wanted it as 4 by 16, so on. Now, if I look at the function, it is nothing but, if I am talking of 4 tosses altogether, I am getting x number of successes. So I can take it as 4cx divided by 60. I can write this as a function. So I'll simply write it as f of x. If I have to write it as a probability distribution function, I'll write it as f of x is 4cx by 16 for x equal to 1, 2, 3, 4, that's it, 0. 0, 1, 2, 3, 4, and 0 otherwise, equal to 0 otherwise. Now if it has to be a probability distribution function, So each probability should be greater than or equal to 0. Sum of all probabilities should be equal to 1. Let's look at the second one so that you can get the understanding of it. Check whether the function given by f of x equal to x plus 2 by 25 for x equal to 1, 2, 3, 4, 5. So let me take x taking values 1, 2, 3, 4, 5. The probability of x equal to x, probability of x equal to 1 is 1 plus 2 by 25, which is 3 by 25. So probability of x equal to 2 is 4 by 25. Here it is 5 by 25. Here comes 6 by 25 and here it is 7 by 25. So probability of f of x equal to x plus 2 by 25 is something like this. So you see each individual probability is greater than or equal to 0, and along with that the sum of all the probabilities over all the possible values of the random variable 3 by 25 plus 4 by 25 so on. 3 plus 4 7 plus 5 12 plus 6 18 plus 7 25 by 25 making it 1. So even the second rule where the sum of all probabilities should be equal to 1, even that is getting satisfied. So this I can very well treat it as a probability distribution of a discrete random variable. Then in the context of probability distribution, we also have what is called as a probability histogram. So we are simply plotting a graph where we have, let's say in our earlier example, the different values of the random variable. So let's say we are talking of heads, number of heads. So there is a possibility of 0 heads, 1 head, 2 heads, 3 heads, 4 heads. And here I'll take the probabilities. So for 0 heads, it is 1 by 16. For 1 head, it is 4 by 16. For 2 heads, it is 6 by 16. For 3 heads, again, it is 4 by 16. And for 4 heads, it's 1 by 16. So this kind of a graph that we are creating, where we are taking the different values of the random variable and the corresponding probabilities on the y-axis, this is called as a probability histogram. But here each of the heights is equal to the probability, and generally we take this as the midpoint. One is not this one is the midpoint of this. So this is 2, this is 3, and this one is 4. So the graph is plotted more in this way. Now many a times we take rectangles and say height is equal to that of height is what is equal to the probability, but in many cases we can also use areas to the probabilities. That is what we will be seeing at a later point when we are talking about continuous distributions. The area of the curve, the area and the area is what is typically, instead of height, the area under the graph is typically taken as a measure of probability. So for all continuous distributions, we could see that the area is taken as the probability. So even here, we can very well go ahead with the mechanism of considering the area instead of the height being called as a measure of probability of that particular value associated with the random variable. Now, moving on to the next topic within this, wherein I am interested in a distribution function associated with the same random variable, discrete random variable. Otherwise, we also call as a cumulative distribution of x. So, we have already got f of x equal to 4cx by 16. And probabilities wise also, we have got 1 by 16, 4 by 16, 6 by 16, 4 by 16, and again 1 by 16. Now, if I really have to talk about a cumulative distribution of x, it is nothing but it's the probability that the value of the random variable is less than or equal to some real number. Probability x less than or equal to 2. It means it is same as probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2, which is otherwise 1 by 16 plus 4 by 16 plus 6 by 16, making it 11 by 16. So the cumulative distribution function f of x is nothing but it's the probability of x less than or equal to x, which is nothing but we are adding the individual probabilities up to the value of x. All the individual probabilities up to the value of x. That is what we are calling as the distribution function. So values of f of x, again if you are talking about some of the important properties associated. So here if you see, small f of x is generally associated with individual probabilities, but capital F of x, when we are seeing the notation, it is more and more associated with the cumulative distribution function. And whenever we are using the word cumulative, we are referring to x less than or equal to x. So some of the important things, f of minus infinity, right? It should be 0 because there is no other value less than or equal to minus infinity. X cannot take any value less than or equal to minus infinity. So that's where the f of minus infinity should be 0. Similarly, f of plus infinity should be 1 because there can't be any value that could be greater than infinite. So f of infinite, which is probability of x less than or equal to infinite, is again equal to 1. And couple of other rules. If a is less than b, then f of a should be less than or equal to f of b. So it's as good as saying if 2 is less than 3, probability capital F of 2, which is nothing but probability of x less than or equal to 2, and f of 3 is probability of x less than or equal to 3. What it says is probability of x less than or equal to 2 should always be less than or equal to the probability of x less than or equal to 3. So that is one more rule that we really need to be comfortable with. So define not only for the values that are taken by the given random variable, right? When we are defining f of x, we are not just defining for that particular values that are taken by the given random variable. Generally we define for all the numbers. So when I say f of x, in this case, for this example, f of x is nothing but I'm adding up all the probabilities. So I could very well specify f of x is 0. So if I have to take the same example of the balanced coin, if I have to solve it, it's nothing but f of x is 0 for x less than 0 is equal to 1 by 16 when we are talking of between 0 and 1 is equal to 5 by 16 when we are talking of x anywhere between 1 and 2 is equal to 11 by 16 when we are talking of x anywhere between 2 and 3, 15 by 16 when we are talking of x anywhere between 3 and 4, and 1 for any value of x which is greater than or equal to 4. Now this is what is the way we represent a distribution function. right? We have to do it in this way for all specific values. So we are not just defining for those values which are obtained, which are the values that are taken by the random variable, but we would be typically considering for almost all the observation. So for all the possible values is what we would be generating this distribution function. So that's one more comfort level that we really need to carry. If the range of the random variables x consists of x1 less than equal to less than x2 less than x3 so on, if you are finding, so here if you are talking about the random variables, x1 is 0 in toss of coin, 0 less than 1 less than 2 less than 3 less than 4, f of 0 is equal to capital F of 0. Right, this is what we got. F of 0 was 1 by 16. Even capital F of 0 we have given it as 1 by 16. Then I can very well find out the remaining things from here. I can get my F of 1 as 5 by 16 minus 1 by 16, which is 4 by 16. I'll get F of 2 as 11 by 16 minus 5 by 16, which is 6 by 16. F of 3, so the individual variable, what is the probability that it takes an individual value, 15 by 16 minus 11 by 16, making it 4 by 16, and f of 4 I'll get it as 1 by 16. And finally f of 5 I'll get it as 0 because for 5 and 4 both of them it is f of 5 and f of 4 both of them are 1, 1 minus 1 is making it 0. So I can very well find out small f of xi is nothing but capital F of xi minus capital F of xi minus 1. That's one more way of quickly executing the probability functions from their corresponding distribution function. Alright. So now we would move on from a discrete variable case to a continuous random variable case. So when we talk about continuous random variables, they take the values on a continuous scale. So it's not that x will be taking only 1, 2 or 0, 1, 3, 4, but it can take any number of values. So x can take on a continuous scale of value. So the outcomes of the experiment, if you are looking at, if I'm talking about this as a line or a line segment, the values that the random variable might take could be any of these things rather than just a quick discrete set of points. Now, because almost any possible value is possible to be taken, all these values are possible on this within this range. If I want to talk about the probability of one single point, it's almost 1 out of infinite possible outcomes that are there, which will make it equal to 0. So this is one thing we have to understand when we are working with continuous random variable. Probability of an event occurring in a very small interval is almost, or if I am talking about a point to be specific, not even an interval. If I'm talking of a point, it is very much negligible because there are infinite set of values that are possible, and out of them I'm looking at one as favorable. So the probability of that one single point in case of a continuous random variables is always 0. So that's one thing we have to always remember. When we are assigning a probability to an individual points working out with continuous random variables, we always assign a probability of 0 to the individual points. Right? That's one more important point that we really need to understand. Having understood the continuous random variables, let's go on to try to understand the probability density functions associated with the continuous random variables. So, when we are talking about probability density functions, we are mentioning the area under the curve. So, we are plotting this being an interval, right? The interval is taken on the horizontal axis, the interval which the values which the random variable could typically take as values. And instead of plotting the heights like your histogram in case of discrete, we will take a curve. The area underneath the curve will give you the probability, and that is what we are calling as a probability density function. It's a kind of an expression, the graph of which if we plot, we get the area under the curve giving me a probability uh, giving me the probability density associated with that particular function. So definition of probability, if I have to define a probability for this particular random variable, I presume that for each random variable a probability density function is existing. So once I know the probability density function, right, the probability density function is the equation associated with this kind of a shape. I'm plotting that probability density function by taking the interval along the horizontal x-axis and the corresponding probabilities along the y-axis, giving me a kind of a smooth curve like this, and the area underneath the curve is what is associated probabilities corresponding to that random variable. So wherever I have to define the probability in case of continuous variables, I assume that for each random variable a probability density function is existing. And once I have my probability density function, uh, in order to get the probability of a particular range, because we have already discussed that the probability of one single value, one single point in case of continuous is 0. Probability of x equal to x is always 0 because there are infinite possibilities, and out of which I am talking about one single possibility. So probability of a specific pointed value occurring is always 0. So we always talk about the probability associated with an interval when we are working with continuous random variables. So we have a probability density function. We are integrating it from a to b, and whatever the value that we get, that is the probability that is corresponding to that random variable within the interval a to b. So that is how we typically work out when we are computing the probabilities associated with the continuous variables. We are taking a PDF, and that particular PDF we are integrating between A and B. So if I am integrating this PDF between 15.9 and 16 will give me what is the probability that this random variable will take a value between 15.9 and 16. So this is how we get probability of A less than or equal to X less than or equal to B. So I'm taking the probability density function f of x, which was what we have called as a probability distribution function in case of discrete. I'm using a word called probability density function here, f of x, small f of x, which is individualistic points. So I'm taking this particular function, integrating it between a and b for any real constants a and b, and a less than or equal to b. So always remember, in case of continuous case, probabilities are always associated with intervals. We will not define the probability for a point. So for a point there is no meaning. We are always defining probabilities associated with the interval. So because of this particular reason, even if I say probability of A less than or equal to X less than or equal to B, or I say probability of A less than or equal to X less than B without including equal to here, probability of A less than X less than or equal to B, or even probability of A less than X less than B. All four probabilities will be the same in case of continuous, because what is missing out here is only one point called B, and anyhow we know that the probability of that point is 0. Here also what is missing out is A. So the point, one point. Here also 2 points are missing. So all these probabilities will remain one and the same. Right? Because X is a continuous random variable, we are only interested in looking at the probabilities within a range of values. So the probabilities associated with one single points are always zeros. So any of these four will result in the same answer itself. So the probabilities are always associated with the intervals. So f of x is the value of a probability density, not the probability density of x at x. It is within an interval, right? So it's not the probability of x equal to x. It is the value of a probability density within a particular interval. So it does not matter whether we include the endpoints from the interval a to b or not. So whether these are included or not included, both of them will mean one and the same. And coming to some of the properties that are associated with the probability densities, again each individual probability should be greater than or equal to 0 within the range. So it can't be negative. Probabilities cannot be negative at all. Very common rule. And when I am trying to integrate the density function from minus infinity to plus infinity, any density function, it should be equal to 1. So this is a very important, just like the way we said, for in case of discrete, when I am adding up all the possible probabilities within the entire sample space, the sum should be equal to 1. The same logic here, in case instead of sum we replace it with integral, but the concept still remains the same. We are integrating it between minus infinity to plus infinity, which means over the whole range of values possible. So within that range, if I am doing an integration, the value should be equal to 1. So these are some of the common rules that we really need to keep in mind before solving any of the numerical problems associated with continuous random variable. So let's take one simple numerical to get started. If x has a probability density f of x equal to k into e to the power of minus 3x for x greater than 0 and it is 0 elsewhere. Find k. So first thing I have to find k. And once I know the k, I want to find what is the probability that the x will lie between 0.5 and 1. So this we can very well find by doing the integration. But for the first thing, if I want to find my k, I have to first make use of my one of the properties saying within the entire interval, when I am integrating across minus infinity to plus infinity f of x dx, it should be equal to 1. So this is one rule that I would like to use, right? Now anyhow, we know that it is from 0 to infinity only. So I'll change this instead of minus infinity to infinity. I'll change it from 0 to infinity k e power minus 3x dx. This should be equal to 1. So I can very well find out k into e power, the integration of e power minus 3x is e to the power of minus 3x by minus 3. This I am taking it between infinity to 0. This should be equal to 1. So I'll take the constant out, minus k by 3 times e to the power of minus infinity 0 minus e to the power of 0 1 is equal to 1. So k by 3 into minus 1, which is k by 3 equal to 1, making it k equal to 3. So for this I have got my value of k as 3. Then now I should be able to find what is the probability of zero point 0.5 less than or equal to x less than 1. So I am integrating between zero point 0.5 and 1, 3 e power minus 3x dx. So the integral for this 3 into e to the power of minus 3x divided by minus 3. This I am integrating between 1 and zero point 0.5. So this is minus 1 times e to the power of minus 3 minus e to the power of minus 1.5. So which is nothing but e to the power of minus 1.5 minus e to the power of minus 3. I should be able to find out e to the power of minus 1.5 minus e to the power of minus 3, which will give me that the probability for this particular random variable taking a value between zero point 0.5 and 1. So we have used the first rule saying across the range the probability should be equal to 1. Based on that we found out the value of k and use that value of k to find the probability within a specific interval. Now here also, just like the way we had a cumulative distribution function in case of a discrete, where we said f of x is nothing but probability of x less than or equal to x, the same fundamental continues even in case of continuous as well. So when I'm talking about x is a continuous random variable, probability density is f of t. I can very well integrate this f of t from minus infinity to x, just like the way we have summed all the probabilities up to x, all the probabilities less than or equal to x. When in case of discrete to get the continuous distribution, here also we are doing an integration of the density function across all the values from minus infinity to x to get the cumulative distribution function associated with the random variable. And here also the same set of rules are applicable. F of minus infinity will be 0 because probability of x less than or equal to minus infinity cannot exist, so it would be 0. Probability of plus infinity is always 1, right? The cumulative distribution function of plus infinity is always 1. Probability of x less than or equal to infinity, all possible values should be there, so it's always equal to 1. And when we are talking of a less than b, probability the cumulative distribution function f of a should always be less than or equal to f of b. So these kind of rules are already the similar to what we have seen in case of discrete. And one small thing, in case of discrete, when I had f of x, f of xi, I have taken it as f of xi minus f of xi minus 1. That is what we have done to get densities from the distributions, individual probabilities from the distribution functions in case of discrete. Whereas here, if I am saying small f of x is the density function and the capital F of x is the distribution function, the probability that a is lying between, x is lying between a and b, I can very well take the difference between the two distribution function. Once I have the probability, the distribution function of b, distribution function of a, by doing a subtraction between the two, I can find the density value lying between a and b. And once I have the distribution function with me, from the distribution if I have to take the density function, it's as good as I'm taking the derivative of that particular distribution function to arrive at the density function. Let's take a couple of examples to get a slight amount of hold in terms of working with the density functions and the distribution functions. Find the distribution function of the random variable x for this example itself, right, and use it to reevaluate 0.5 less than x less than 1. This is an interesting question. First, let me find out the distribution function for this. We have already got k is 3, right? So let's take minus infinity to x f of t dt. This is what will be my distribution function. Now I know this is not minus infinity because x is taking the values only from 0, so I'll say 0 to x. So I'll take it as 0 to x 3 e power minus 3t dt. This is what is my distribution function, right? I'm taking this as capital F of x. So which is coming out as 3 e power minus 3t by minus 3 and substituting it x and 0. So minus 1 times e power minus 3x minus 1. So basically it's like 1 minus of e to the power of minus 3x. So the distribution function in this case is 1 minus e to the power of minus 3x. This is the distribution function, so which means if I have to write the distribution function, I have to write it for everything. So I'll say it is equal to 0 for x less than or equal to 0. It's equal to 1 minus e to the power of minus 3x for x greater than 0. Now we have already said we have to find now 0 probability of 0.5 less than or equal to x less than or equal to 1. So which is as good as saying it is the same as f of 1 minus f of 0.5. F of 1 is 1 minus e to the power of minus 3. F of 0.5 is 1 minus e to the power of minus 1.5, which will work out very clearly as e to the power of minus 1.5 minus e to the power of minus 3. This is what is the same solution that we have got earlier as well. So one, I can find out the distribution function, and based on that I can find out the range, the probability of random variable taking values within a specific range. Is this fine? Alright. Now let's look at one more example. Find a probability density function for the random variable whose distribution function is given like this. So we are having a distribution function here. F of x is 0 for x less than or equal to 0. It is x between 0 and 1, and 1 for x greater than or equal to 1. Right? So we can very well get. So we are talking about the density function. So we have to do a differentiation to get the density function. So it is differentiable everywhere except where x is equal to 0, and it is not differentiable where x equal to 1. So we differentiate for x less than 0. So taking a derivative of this is all constant. So the derivative is 0 itself. Derivative of x is 1. Derivative of 1 is 0. So I am getting my f of x, which is the derivatives, saying for x less than 0 it is 0. For x lying between 0 and 1, the f of x is 1, and for x greater than 1, the f of x is 0. Now this is where you could say we can very well create f of x equal to 1 when x is lying between 0 and 1 and it is 0 elsewhere. So that is how you could create a density function vis-a-vis a distribution from a distribution function. So that's how you can typically start evaluating the numericals associated with the continuous random variables. Now, when we look at discontinuous distribution functions, the random variables are very much mixed. If you look at something like this, so the random variable from 0 to per x values between 0 to 0.5, it is a smooth function increasing. Suddenly there is a discrete part at zero point 0.5. We have a discrete part because it is discontinuous here, and again from zero point 0.5 to 1 onwards it's again continuous. Now these are the discontinuous distribution functions where the random variables are mixed. The random variable is not either fully discrete or fully continuous. So discontinuous at each point having a non-zero probability. So this point there is a non-zero probability occurring. So this is where it is discontinuous and it is continuous elsewhere. And if you are talking about the height of this particular step 1 by 4 to 3 by 4, which is 0.5, it is giving the probability that the random variable will take on that particular value. So the probability that x equal to 0.5 is 0.5 here. So this is what we are calling as a mixed distribution, where across it could be continuous, but at one or a few specific points my random variable would be more discrete. So this is one more thing that we really need to understand with respect to the continuous random variables. But if you are talking about a regular distribution function which are fully continuous, you will find something, they are keeping on increasing or stable, but after a certain point they reach out, they flatten out at 1. So there are no discontinuities anywhere in between. So those are the regular distribution functions. But when you are talking about a discontinuous distribution function, we'll see these kind of gaps in the middle. Alright. So till now we have looked at the univariate distribution, univariate random, one single random variable, whether it is continuous or discrete. Now we will start trying to understand the distribution, densities, etc. associated with two variables taken together. So this is what we are calling as bivariate distribution. So there are situations, lot of business related examples where we are interested in evaluating the relationship between a pair of random variables, right, at the same time, not individually. We are interested in looking at both of them together. So this kind of a scenario is what we are calling as a bivariate distribution. Those kind of situations where we are interested at the same time in a pair of random variables. We are always looking at them as a pair rather than their individual occurrences. So instead of simply saying probability of x equal to x, we will start talking of probability of x equal to x and y equal to y. So x and y, I can take them as discrete random variables. So if there are two different discrete random variables, I am interested in seeing what is the probability that x will take on the value of small x and y will take on the value of small y. So we are moving away from the univariate case to a bivariate case, taking two of them together. The same thing I extend to multiple variables instead of just two of them. I'll call it as a multivariate case. Okay, so we are interested in the intersection of the events, probabilities associated with x taking x, y taking y. Probably the example would be more clear for you. Two caplets are selected at random from a bottle containing 3 aspirins, 2 sedatives, 4 laxative caplets. So out of these 9, I am selecting only 2 of them. So out of 9, if I have to select 2, it can be done in 9C2 ways, which is nothing but 36 ways. Fair enough. If X and Y are respectively the number of aspirin and sedative caplets included among the 2 caplets drawn from the bottle. So we are talking of X and Y as random variables, number of aspirins that I am drawing, number of sedatives that I am drawing among the 2 caplets drawn from the bottle. Find the probabilities associated with all possible pairs of values. Okay. Now if you see X, Y, right? So X can take 0, right? There could be 0 aspirins, there could be 1 aspirin, or there could be 2 aspirins. Similarly, when I am talking about sedatives, there could be 0 sedatives, 1 sedative, 2 sedatives. So all these are possibilities. So this is what we are calling as the joint distributions or the joint probabilities associated with X and Y. Now what is the probability that X is 0, Y is also 0? Mean there should not be any aspirin, there should not be any sedatives. So the 4 that are picked are from the laxatives itself. So 4C2 ways in which 2 can be picked from 4. So this will give me a 6 by 36 kind of a probability. Now what is the probability of having 0 aspirin and 1 sedative? So if I have to look at 0 aspirin and 1 sedative, automatically out of this 2 there should be 1 that is selected, which can be done in 2C1 ways, and out of the remaining 4 again 1 needs to be selected, which should be in 4C1 ways. So 8 by 36, right? We are talking about 0 aspirins and 1 sedative, which would work out as 8 by 36. Then if I want to see 0 aspirins and 2 sedatives can be taken only in one way, so which will make it 1 by 36. Then I require 1 aspirin, 0 sedatives, 1 aspirin, I'll take it in 3C1 ways. And so because there is no sedative, I have to pick 1 from the remaining laxative, which is in 4C1 ways, making it 12 by 36. Then I'm talking about 1 aspirin, 1 sedative, 1 aspirin and 1 sedative, 3C1 into 2C1, 6 by 36 ways. 1 aspirin and 1 sedative can be picked. 1 aspirin and 2 sedatives, it can't be picked at all because I'm picking only 2 of them altogether. Then 2 aspirin, 0 sedatives. So 3C2 ways, making it 3 by 36. 2 aspirin, 1 sedative cannot be picked. So these are all zeros because that's not possible. I can't pick more than 2. So this is how my table is coming out. 0, 0 is 3 by 36, 8 by 36, 1 by 36, 12 by 36 and 6 by 36. So altogether when I am trying to find out the total 6 plus 8, 14, 15, 15 plus 12, 27 plus 6, 33 and 33 plus 3 is 36. So overall it's working out to 1. So probabilities associated with all possible pair values of X and Y. So these are the possible values. Now in this context I can very well define the joint probability distribution associated with X and Y, wherein I am trying to find out f of xy, saying p of x equal to x and y equal to y for each pair of values of x and y. Right, so you could very well generalize it here, saying if I have to make a generalized f of x comma y here for this example, okay, so x is number of aspirants, so I can say 3cx, y is number of sedatives, I can say 2cy, and z is the remaining, so I can say 4c 2 minus x minus y, and divided by 9c2, which is 36. So this I can generalize it as a joint probability distribution function associated with x and y. Right? I can very well, but I can say x is 0, 1, 2, y is also 0, 1, 2, and x plus y should lie between 0 and 2 itself. So these are some of the additional conditions I can put. X could be any value 0, 1, 2. Y could be any value 0, 1, 2. X plus y should lie between 0 and 2. So that's the way I'm handling their joint probability distribution. And the conditions, yes, each individual probability should be greater than or equal to 0 for each pair of x and y. And when you are summing up the probabilities across the entire domain, the sum of probabilities should be equal to 1. We have already done that summation. We have seen it is 36 by 36 equal to 1. So again, a quick example with the usage of that specific concept. Determine the value of k for which the function given by f of xy equal to kxy, where x is 1, 2, 3, y is 1, 2, 3, can serve as a joint probability distribution function. So I am taking x and y. F of x comma y is kxy. So you look at 1, 1, so it becomes k into 1 into 1, which is k. 1, 2 is 2k. 1, 3 is 3k. 2, 1 is 2k. 2, 2 is 4k. 2, 3 is 6k. 3, 1 is 3k. 3, 2 is 6k. 3, 3 is 9k. So the sum of all these probabilities should be equal to 1. So 6k, 8, 12, 18, 21, 27, 36. So coming out 36k equal to 1. From here I am getting my k as 1 by 36. So this is how we can very well take this as a joint probability distribution function, and based on that we can try calculating the values. Then the joint distribution function, just like the way we have evaluated the distribution function individually, we are also looking at the joint distribution function. If x and y are discrete random variables, we are talking of capital F of xy as a cumulative distribution function, wherein p of x is less than or equal to x, p of y is less than or equal to y, and so we are summing up all the individual density functions, individual probability functions, where x is less than or equal to x and y is less than or equal to y. So that is what we are calling as a joint cumulative distribution of x and y. So you want f of 1 comma 1 for the drugs example, right? So the drugs example, let me take x 0, 1, 2, y also 0, 1, 2. So 0, 0 we got it as 3 by 36. 1, 0, 1 we got 8 by 36. 0, 2 we have got it as 3 by 30, no, 0 of, so 1 by 36, 0 of 0 of aspirin and 2 of sedatives. So here we have got 12 by 36, 1 aspirin and 0 sedatives. So 12 by 36, this is 6 by 36 and this is 0. And this we have got it as 3 by 36. So just let me use the same example. So find f of 1, 1. So probabilities of x less than or equal to 1, y also less than or equal to 1. So which means I can use these four things only. This is where I am getting my probabilities of x less than or equal to 1, y also less than or equal to 1, making it 18 plus 8, 26 plus 6, 32. 32 out of 36 or 8 by 9 is the probability that is associated for this example. So this is how we are handling the discrete variables, right? In case of discrete, this is how we go ahead in terms of solving the problems associated with joint distribution functions. But now we will move on to the continuous case. So when we are working with the continuous case, we are using the word joint probability density function. So a bivariate function values f of xy is called as a joint probability density function associated with the continuous random variables x and y if I am able to integrate it, if I am able to integrate f of xy across dx and dy. So with respect to x, with respect to y in the xy plane, that is what we are calling as the joint probability density function. So we have this as a joint probability density function. We should be able to integrate it for any region A in the xy plane. Then we are calling this as the joint probability density function. And as the properties are very much similar, the individual probabilities should be greater than or equal to 0. So for any value of x, any value of y, the f of xy should be greater than or equal to 0. And when I am trying to integrate this density function over x and y both across minus infinity to plus infinity, the overall integral should be equal to 1 itself. So these are some of the very common rules which we have been using in case of discrete, in case of univariate variables. So in all these cases the same set of rules are being used, so we are continuing them even for the continuous case as well. So let's solve a couple of examples here to get a basic hold on the usage of bivariate distributions. Given the joint probability density function f of xy is equal to 3 by 5x times y plus x. This is what we are calling as a density function for 0 less than x less than 1. So x is lying between 0 and 1, y is lying between 0 and 2. And this is 0 elsewhere. So this is what we are calling as the density function. Right? A is the region where we are talking of x lying between 0 and 5, 0 and 0.5, y lying between 1 and 2. So we want to find out what is the probability of xy with the area A as a region. So overall this is the density function, and from here I want to find out what is the probability that x is between 0 and 0.5 and y is between 1 and 2. So I can very well integrate because I know that this is a joint probability density function. But if I have to really prove that it is a joint probability density function, I have to integrate it over the entire interval and see that the total probability is 1. So I have to integrate it over this entire interval. So dx dy. So let me get started to see whether this is equal to 1 to really prove whether this is a probability density function or not. And after that I can very well evaluate between the 0 and 0.5 and 1 and 2, right? So let me take, expand each one. So this is between 0 to 1, 0 to 2. It is 3 by 5 xy plus 3 by 5 x square dx dy. So first I can integrate it with respect to x, right? So this one will become, y will still continue 0 to 2. X I will, with respect to x I will take the integration So it becomes 3 by 5y, and 3 by 5y times, so this becomes x, so x squared by 2 between 1 and 0. Then similarly 3 by 5 times x squared integral is x cubed by 3. This is also, so let me take a blank sheet so that we can do this much better. Let me take it here. So I would like to integrate between 0 and 1, 0 and 2, 3 by 5 xy plus 3 by 5 x squared dx dy. So the same thing, now let me do it with respect to x first. So it becomes 3 by 5 y, and the integral of x is x squared by 2 integrated between 1 and 0 plus 3 by 5 x cubed by 3, again integrated between 1 and 0 dy. So this would be remaining as 0 to 2 times 3 by 5 into 1 by 2 minus 0. So 3 by 5 y into 1 by 2, which is 3 by 10 y, and this is 3 by 5 into 1 by 3 minus 0, which is 1 by 5 dy. Now we are integrating this part. 3 by 10 times y is y squared by 2 integrated between 2 and 0 plus 1 by 5 into y again integrated between 2 and 0. So overall is coming out as 3 by 10 times 2 square by 2, 4 by 2, which is 2, plus 1 by 5 into 2, which is 2 by 5. So this is becoming 3 by 5, then this is becoming 2 by 5, overall it is 1. So it's a probability density function for sure. Now we are trying to evaluate, right, probably by integrating between x is 0 and zero point 0.5 and y is between 1 and 2. I am trying to evaluate 3 by 5 xy plus 3 by 5 x squared dx dy. So taking the solving with respect to x first, so y will still remain here, 3 by 5 y into x squared by 2. X squared by 2 is evaluated between 0.5 and 0. 3 by 5 into x cubed by 3 evaluated between 0.5 and 0 dy. So I'll be getting 0 to 2, 3 by 5 y into x squared, 0.5 squared. So 0.5 if I take it as 1 by 2, right, or even this 2 I'll take out, so making it 3 by 10 y, x squared, 0.5 squared, 0.25 or 1 by 4, plus this also I'll take out, making it 1 by 5 times 1 by 5 times x cubed, 1 by 8 dy. So this is being made as 3 by 40. Y I can now integrate it, y squared by 2 between 2 and 0 plus 1 by 40 into y between 2 and 0. So I'll get this as 3 by 40 times 2 squared by 2 is 2 plus 1 by 40 into 2. Overall I'm getting it as 8 by 40, 6 by 40 plus 2 by 40. Okay, y I have to integrate between 1 and 2, not between 0 and 2, right? So I am integrating it between 1 and 2, making it 3 by 40 times 2 squared by 2, which is 2, and 1 squared by 2 is 1 by 2. So this becomes 2 minus 1 by 2, which becomes 3 by 2, and this becomes 1. So overall it is becoming 9 by 80 plus 1 by 40, making it 11 by 80. So this is the probability that this random variable will be taking the values x lying between 0 and half and y lying between 0 and 1 and 2. So you can very well, by just going ahead with a very quick simplification, we can very well go ahead with that particular aspect altogether. So this is how we are computing the joint probability based on the joint probability density function. We are evaluating the probability of a specific range of values. Then we are also talking about a joint distribution function. If x and y are continuous random variables, so distribution function always is capital F of xy, where we are talking of probability of x less than or equal to x, y less than or equal to y. So integrating between minus infinity to y, minus infinity to x, f of st ds dt between minus infinity and minus infinity to plus infinity. So f of xy, if I want from the distribution function, if I want the density function, I'll take the partial derivatives associated with x and y. So from there, from the joint distribution function, I'll get the joint density function for all the points where the joint density is continuous. So let's look at a couple of examples which can really help us to solve these kind of problems. If the joint probability density of x and y is given with this, right, x lying between 0 to 1. So I want to find out the joint distribution function. This is the density function where f of xy is x plus y for x lying between 0 and 1, y also lying between 0 and 1, and it is 0 elsewhere. So we can very well get that because x is greater than 0 and y is also greater than 0. So for computing my f of xy, let me again take a new screen, that would be better. So I can very well consider for x less than 0, y less than 0, I can very well say f of xy is 0. For x greater than 1, y greater than 1, I can very well say f of xy is 1. So I could very well look at only between 0 and 1. So this is where I can say 0 to x, 0 to y. And I'm talking of x plus y, so let me take s plus t ds dt. Right? So let me find out, first let me integrate it with respect to s, with respect to x. So it will be 0 to y, x is s for me. So s becomes s squared. I am taking t as a constant, dt, and so I am integrating it with respect to s squared by 2, and t becomes ts. This I am integrating it between x and 0. So it is 0 to y, x squared by 2 plus xt dt. Now I'll integrate it with respect to t. So this becomes x squared by 2 into t integrated between y comma 0 x into t squared by 2 integrated between x and 0, y and 0. So this becomes x squared by 2 times y, and this becomes xy squared by 2. So the other way I can write it as xy by 2 times x plus y. So this is what comes out as my f of xy. Right? I am integrating it within that specific region. So as long as the value is between 0 and 1, right, x lying between 0 and 1, y lying between 0 and 1, I'll get this as the zone. But now if I want x greater than 1 but y lying between 0 and 1, because we have to take all the interval, x less than 0, y less than 0, I have taken f of xy is 0. X lying between 0 and 1, y also lying between 0 and 1, I have got f of xy as this much. Now I am taking x greater than 1 but y lying between 0 and 1. So I can very well take, so x is greater than 1 means I am considering the whole of from 0 to 1, right, because there is no point in considering up to infinity because x is going up to, x is taking values only up to 1. So x I am integrating over the whole range, but y I am integrating only up to y. So the same s plus t ds dt. So I can very well integrate first with respect to x, which is s. I'll integrate with respect to s, making it s squared by 2 plus ts, everything between 1 and 0 dt. So this is becoming 1 by 2 plus t dt. So this is becoming t by 2 plus t squared by 2 integrated between y and 0. So this works out to be y by 2 plus y squared by 2, which is 1 by 2 y by 2 times 1 plus y. So this would be the region, this would be the area when x is greater than 1 and y is lying between 0 and 1. Similarly, I can very well find out for x lying between 0 and 1. So then I'll integrate it between 0 to x. Y lying between, y is greater than 1 means I'm integrating it for the whole of 1. Then again s plus t ds dt. So this is becoming s squared by 2 plus ts integrated between x and 0, right, and this is again from 0 to 1 dt. So making it x squared by 2 plus xt, and this is integrated between 0 and 1, right. The other way now, because I am integrating it with respect to t, it would be x squared by 2 times t. T is between 1 and 0, so it is 1. Then x times t squared by 2 again between 1 and 0 becomes 1 by 2. So x squared by 2 plus x by 2. So it is becoming 1 by 2 x into 1 plus x. Now this is when x is less than or equal to 1. X is lying between 0 and 1. Y is greater than 1. And if both of them are greater than 1, I can very well integrate it. I should be getting a value equal to 1. So these are all the things that I am putting as a part of my distribution function. When x is less than 0, y is less than 0, the f of xy is 0. When x and y both of them are lying between 0 and 1, the f of xy is xy by 2 times x plus y. When x is less than or equal to, x is lying between 0 and 1, y is greater than or equal to 1, it is 1 by 2 times x into x plus 1. And if y is less lying between 0 and 1, x greater than or equal to 1, f of xy is working out as 1 by 2 y into y plus 1. And if both of them are greater than or equal to 1, the overall capital F of xy is working out to be 1. So this is how from a density function, given from the density function, if I have to find out the distribution function, this is the typical mechanism that we are going to follow. Then look at one more. Find the joint probability density function of the two random variables x and y whose joint distribution function is given by this. So the distribution function is given. From here I want to find out the density function, and from there I also say the joint probability density to find out what is the probability that x will take values between 1 and 3, y will take values between 1 and 2. So from distribution, if I have to find the density, I have to resort to the partial differentiation, right? So let me do this. I'm getting f of xy. So let's do for x greater than or equal to 0, x greater than 0, y greater than 0. 1 minus e power minus x multiplied by 1 minus e to the power of minus y. So we'll take the dou square f by dou x dou y. For this we are trying to find out. So first let me take it with respect to x. Then y is constant, so I'll take it as dou by dou y times. I'm doing it with respect to x, so it becomes 1 minus e to the power of minus y. And what is the derivative of x here? E to the power of minus x minus 1. So which becomes e to the power of minus x, right? Because the derivative of this is e to the power of minus x, and the derivative of x is minus 1, so it becomes e to the power of minus x. Now the same thing, when I am doing it with respect to minus y, it is e to the power of minus x into e to the power of minus y, making it e to the power of minus of x plus y. This is the density function. So it is coming out that f of x comma y will be e to the power of minus of x plus y, where x is greater than 0 and y is greater than 0, and in all other cases it is equal to 0. That is how we are giving. And now if I want to find out the probability that x is lying between 1 and 3, y is lying between 1 and 2, I'll integrate the density function. So x between 1 and 3, y between 1 and 2, e to the power of minus of x plus y dx dy. So I can very well integrate first with respect to x, right? This is nothing but e to the power of minus x into e to the power of minus y. So I can very well integrate with respect to e to the power of minus x into e to the power of minus y. I'll take x, so y will be constant, e to the power of minus y into e to the power of minus x. The derivative is, the integral is minus e to the power of minus x. So which I am integrating it with respect to x, taking values 3 and 1. So it comes out as integral between 1 and 2 e to the power of minus y times minus of e to the power of minus 3 minus e to the power of minus 1. So I'll take the minus out, saying e to the power of minus 1 minus e to the power of minus 3 dy. So I'll simply take this one out, right? E to the power of minus 1 minus e to the power of minus 3. I'll now integrate it with respect to y, making it e to the power of minus y divided by minus 1. So I'll take the other way when I'm taking it between 1 and 2. it is e to the power of minus 1 minus e to the power of minus 3 multiplied by e to the power of minus 1 minus e to the power of minus 2. So you could very well solve this and say what is the probability that the value lies between 1, x lies between 1 and 3, y lies between 1 and 2. So that's how we extend we can very well find out the density functions from the distribution functions, distributions from the densities, all sorts of possibilities we have taken up as different kinds of examples out here, right? Now that we are comfortable regarding the bivariate distribution, the same concept, the same definitions which we have used in case of bivariate, I can very well generalize to the multivariate case, wherein instead of 2 random variables, I am talking of n random variables. You could see here the probability distribution function P of x1 equal to x1, x2 equal to x2, so on, xn equal to xn. When I talk about the cumulative distribution function, capital F of x1, x2, xn, we are talking of probability of x1 less than or equal to x1, x2 less than or equal to x2, so on, xn less than or equal to xn. So this is what is typically working out in case of multivariate. This is in discrete case. And if you look at the continuous case, so the probabilities are obtained by integrating the joint probability density function. The concept is still the same, right? You could see capital F of x1, x2, xn. I'm integrating from a minus infinity to xn, minus infinity to x2, x1, all the density functions, which is what is giving me the distribution function associated with the continuous. If I am given the distribution function, from there if I am taking the density function, I am doing a partial derivative associated with each of the variables. So we can take quick examples, one in the discrete case, one in the continuous case, and try to quickly work out the multivariate distribution. So once we get a quick hold of this multivariate distribution also, then we can then we should be comfortable handling almost all the kinds of aspects. So let me take the example. If the joint probability distribution, right, joint probability distribution of the 3 discrete random variables x, y, z is given like this. F of x, y, z is x plus y times z divided by 63, where x is 1 comma 2, y is 1 comma 2 comma 3, z is 1 comma 2. And we are talking of probability of x equal to 2, y plus z is less than or equal to 3. So x is equal to 2, this is fixed, y plus z is less than or equal to 3. So what are the various possibilities that I can have? So if I talk about x, y, z, x is 2, y plus z is less than or equal to 3. So y could be 1, z could be 1, then y could be 1, z could be 2, then y could be 2, z could be 1. So these are the only possibilities that are existing. So I can very well find out f of 2 comma 1 comma 1 plus f of 2 comma 1 comma 2 plus f of 2 comma 2 comma 1 to solve this expression. So the first one, x plus y times z, 2 plus 1 times 1, which is 3 by 63. Then it is 2 plus 1 times 2, 6 by 63. And finally it is 2 plus 2 times 1, 4 by 63. Overall making it 13 by 63. So this is the probability that x is equal to 2, y plus z is less than or equal to 3. And finally, to see whether it's a joint distribution function or not, the sum of all the probabilities should be equal to 1. So because there are two possibilities here, three possibilities here, two possibilities here, overall I am going to get 12 possibilities, right? X is 1, Y is 1, Z is 1, X is 1, Y is 1, Z is 2. So all these 12 possibilities that are coming out, if I sum them up, I should be getting an overall value of 1. Then it is a joint probability distribution function itself. Now let me take the case of continuous, right? I'm saying a trivariate probability density having three random variables x1, x2, x3. So the probability density function is given by f of x1, x2, x3 is x1 plus x2 multiplied by e to the power of minus x3, wherein we are talking of x1 is between 0 and 1, x2 is also between 0 and 1, but x3 is positive, right? So I want to find out the probability where x1 is lying between 0 and half, x2 is lying between 0 and 1, and x2 is lying between half and 1, and x3 is less than 1. So first of all, okay, here I don't need to really check whether it's a density function or not, but if at all I have to check, I have to integrate over the whole area, right? I have to integrate over the entire area and see if the probability is 1 or not. So if I have to first check whether it's a joint probability density function or not, valid or not, then I'll integrate 0 to 1 for x1, 0 to 1 for x2, and 0 to infinity for x3. Right? So I could very well integrate it x1 plus x2 into e to the power of minus x3 dx1 dx2 dx3. I could have expanded it 0 to 1, 0 to 1, 0 to infinite x1 e to the power of minus x3 plus x2 e to the power of minus x3 dx1 dx2 dx3. Now first let me integrate it with respect to x1, right? So this is between 0 and 1. So the first part, so this will remain 0 to 1, 0 to infinite. Because I am integrating it with respect to x1, it is e to the power of minus x3 times x1 squared by 2. And I am integrating it between 1 and 0, so I'll directly take it as 1 by 2 plus x2 e to the power of minus x3, this whole is a constant, and into x1, integrated between 1 and 0, it is 1 itself. So this becomes dx2 dx3. Then now I'll integrate it between with respect to y. So z is still retained. So 1 by 2 e to the power of minus x3, and that into x2. So integrated between 1 and 0 is lying like this. Then e to the power of minus x3, x2 is integrated x2 squared by 2, which is 1 by 2 again. So this becomes dx3. So 1 by 2 e to the power of minus x3, 1 by 2 e to the power of minus x3, which is e to the power of minus x3 itself. So e to the power of minus x3 is minus e to the power of minus x3 integrated between infinity and 0. So making it minus of e to the power of minus infinity is 0, minus e to the power of 0 is 1, overall it is 1. So this is a very much a possible density function, right? Now if I go ahead and try to solve the problem to find out what is the probability that x1 is less than or lying between 0 and half, so x1 is lying between 0 and half, y1 is lying between half and 1, and z is lying between 0 and 1. So I'm having it as x1 plus x1 e to the power of minus x3 plus x2 e to the power of minus x3 dx1 dx2 dx3. So I could very well integrate with respect to x1. So e to the power of minus x3. So only y and z are left. Half to 1, 0 to 1. E to the power of minus x3. x1 squared by 2 makes it 1 by 4. x2 e to the power of minus x3 into x1 making it 1 by 2. So this is dx2 dx3. Now I'll integrate it with respect to y. So 0 to 1, 1 by 4 times e to the power of minus x3, and because I am integrating it so into x2 between 1 and half, so again it is 1 by 2 plus 1 by 2 into e to the power of minus x3. x2 is integrated x2 squared by 2 between 1 and half. So 1 by 2 minus half squared by 2, 1 by 4 by 1 by 2, which is 1 by 8. 1 by 2, so if I am integrating it here, x2 squared by 2 between 1 and half. So it is 1 by 2, no, 1 by 2 I have already taken out, okay, x2 squared by 2, which will be 1 by 2 minus half squared by 2. Half squared is 1 by 4, 1 by 8. 1 by 2 minus 1 by 8 becoming 3 by 8 dx3. So this is 1 by 8 and 1 by 8 e to the power of minus x3, and this is 3 by 16 e to the power of minus x3. So 1 by 8 into 1 by 8 plus 3 by 16, if I am looking at it, is so 2 by, so it is 5 by 16. Something went wrong. 1 by 2, 1 by 4 into e to the power of minus x3 integrated, okay. So 1 by 2 e to the power of minus x3, x2 is x2 squared by 2, 1 by 2 minus 1 by 2 squared by 2, right, 1 by 2 squared, okay, fair enough. So which is working out to be this much. So 1 by 8 e to the power of minus x3, 1 by 16, 3 by 16 e to the power of minus x3, so it is becoming 5 by 16 e to the power of minus x3, so which is working out to which 5 by 16 e to the power of minus x3. So I am integrating it minus of e to the power of minus x3 integrated between 1 and 0. So it is working out as 5 by 16 into e to the power of 0 is 1 minus e to the power of minus 1. So it is coming out as 5 by 16 into 1 minus e to the power of minus 1. That is the kind of a probability where x is lying between 0 and 1 x is lying between 0 and half, y lying between half and 1, and x3 lying between 0 and 1. So you can very well, if there is some kind of a simplification thing somewhere going wrong, fair enough. But you can very well use your integration skills accordingly to solve the problem in a step-by-step manner. All right. So that's how you solve the multivariate distribution. So the same bivariate distribution is extended to the multivariate case in this particular manner. Now, now we will move on to the slightly next topic, which is where we are looking at marginal distribution, which is also one more important area that we would be using. So when we are talking of x and y, again we have the discrete case as well as the continuous case. So when I talk about the discrete random variables x and y, wherein f of xy is their joint probability distribution at x and y, I am doing a summation across all y for each x. For each x, I am doing the summation across all the y. I call this as marginal distribution of x. So which means I am taking only x and all the y's. So when I am saying probability of x equal to 0, so I am looking at probability of x equal to 0, y is 1, x equal to 0, y is 2, x equal to 0, y is 3. So I am looking at for x equal to 0, I am looking at all possible probabilities of y and summing it up. That is what I call as marginal distribution of x. Similarly, when I am doing a summation across all the x values for each value of y, then I call it as the marginal distribution of y. So just for a quick understanding, let me go ahead with my tablets example, right? So wherein we looked at aspirin, right? X is the number of aspirins. So I'll take 0 aspirin, 1 aspirin, 2 aspirins. Y is the sedatives, 0 sedative, 1 sedative, 2 sedatives. So we got the probabilities as 6 by 36. I'm trying to recap from that example. You can go back and use it. So these are the x values. These are the y values. So x is 0, y is 0. We got it as 6 by 36. This was 8 by 36. This was 1 by 36. And this was 12 by 36. This was 6 by 36. This did not exist. And even this was 3 by 36 and not exist. Now if I want to find out marginal probability distribution, means I want the probability distribution of x alone. When I want probability distribution of x alone, I will sum across all the y's for each x. So for x equal to 0, the marginal distribution is 6 plus 8, 14 plus 1, 15 by 36. Then for x equal to 1, it is 18 by 36. And for x equal to 2, it is 3 by 36. So these are the marginal distributions associated with x. Right? I can find out the marginal distribution of x, wherein I say x equal to 0, the probability is 15 by 16 because I am adding across all the y's for a particular value of x. Similarly, when I say probability of x equal to 1, I am adding all the y's for x equal to 1. Similarly, I am adding all the y's for x equal to 2. So this is the probability distribution of x alone, which is what we call as a marginal distribution of x. Similarly, when I want to know the marginal distribution of y equal to 0, 18 plus 3, 21 by 36. Y equal to 1, it is 14 by 36. And y equal to 2, it is 1 by 36. So when we are doing a column totals, we are getting the marginal distributions of y. When we are doing row totals, we are getting the marginal distributions of x. So that is the way in a discrete case from the joint probability distribution function or joint probability distribution values, I can very well find out the marginal distribution, marginal probability values of x and y. Alright. Then, if I go ahead with the continuous case also, if x and y are continuous random variables, f of xy is the value of their joint probability density function at x and y. We are talking about marginal density of x where you are integrating across all the y. When you are doing an integration of the function across the y for each of the x, so only when you are doing an integration across y, across all the y, minus infinity to infinity, the entire value of y when you are doing an integration, then it is the marginal density of x. When you are doing the integration across minus infinity to infinity with respect to x, then it becomes the marginal density of y. So just for an example, you can take this. F of xy is 2 by 3 times x plus 2y, where x is between 0 and 1, y is also between 0 and 1. I want to find out the marginal densities of x and y. So let me take a white screen for this. So I'm saying f of x comma y is 2 by 3 times x plus 2y, where x is between 0 and 1, y is also between 0 and 1. Now if I want the marginal probability of x, I am integrating this f of xy, right, from minus infinity to infinity, which means across the whole range of y. So I'll integrate it between 0 and 1. 2 by 3x plus 2 by 3x plus 4 by 3y, and I'll integrate it only with respect to y. So it becomes 2 by 3x, y is between 1 and 0, so it is 1, and 4 by 3, y is y squared by 2, 1 by 2. So which is working out as 2 by 3x plus 2 by 3. Right? So I could simplify it as 2 by 3 times x plus 1. This is the marginal distribution of x. Marginal density function of x. Similarly, when I want to find out the marginal density function, probably let me use another function, h of y. So I'll integrate it between for all x. So I'll do it as 0 to 1, 2 by 3x plus 4 by 3y. Now this time I'm integrating it with respect to x. So it is 2 by 3 times x squared by 2, which is 1 by 2, plus 4 by 3y times x, which is 1. So this you could see 1 by 3 plus 4 by 3y. Right? So it comes out as 1 by 3 times 1 plus 4y. This is the marginal distribution of marginal density function of y. This is the marginal density function with respect to x. So we can find out in this way the marginal density functions based on the joint probability density function. And so you can extend the same. Instead of a two variable case, you can very well extend it to the multivariable case also. Right? So you have looked at the earlier example of the trivariate probability density. Right? This example, if I really want to relook at this example again, wherein I want to find out joint marginal density of x1 and x3, and from there I want to find out the marginal density of x1 alone. So if I want, let's look at the example here. right? So the same thing I'm taking f of x1, x2, x3. I'm taking as x1 e to the power of minus x3 plus x2 e to the power of minus x3. X1 is between 0 and 1, x2 is between 0 and 1, x3 is greater than 0. Now first I want to find out joint marginal density of x1 and x3. So I want g of x1 comma x3. So I would like to integrate across all x2. So let me integrate across all x2 this function. So if I am integrating across all x2, which will work out as this is entirely constant x1 e to the power of minus x3. So e to the power of minus x3, x2 is x2 squared by 2, which is 1. So dx2, right? I mean, we have already integrated it. So it is becoming x2 squared by 2, which is 1 by 2. So it is becoming e to the power of minus x3 times x1 plus 1 by 2. So this is g of x1 comma x3. Now I am also asked to find out the marginal density of x1 alone. So if I want to find out h of x1 alone, now I will integrate it with respect to x3. So which would be 0 to 1, this one. So e to the power of minus x3 times x1 plus 1 by 2. So this part is a constant, so I'll take it as x1 plus 1 by 2 times e to the power of minus x3 is minus e to the power of minus x3 integrated between 1 and 0. So which will come out as x1 plus half times, so e to the power of 0, 1 minus e to the power of minus 1. So when I am integrating it across the so x3 is to infinity, right? X3 is lying between 0 to infinity. So probably I should take it like this. So e to the power of 0 minus e to the power of minus infinity, which is 0. So overall comes out as x1 plus 1 by 2. So the marginal joint marginal density function of x1 alone, sorry, marginal density function of x1 alone is x1 plus 1 by 2. Joint marginal density function of x1 and x3, where I am integrating it over the entire range of x2, is working out to be this particular number. So that's how we can simplify the numericals. Marginal and joint marginal distribution functions also, if you have to compute, more or less similar kind of a process to go ahead. So one single clarity, right? If I'm looking at marginal distribution function, so I'm simply integrating it across all the values of y, but x I'm integrating it only with respect to 0 to that particular x value. So the marginal distribution functions are also handled in a much similar manner. I hope you are getting the comfort level in terms of handling the marginal distribution functions very comfortably. Then once we are done with the marginal distributions, our focus moves on to the next aspect, which is the conditional distribution. So moving towards conditional distribution, we have seen in case of conditional probability, the probability of A given B is nothing but probability of A intersection B divided by probability of B. The same logic I am putting in case of random variables also. Probability of x equal to x given y equal to y is nothing but probability of x equal to x comma y equal to y, which is the joint distribution function associated with x and y, divided by probability of y equal to y, which is nothing but the marginal distribution associated with y. So it is nothing but the joint distribution associated with x and y divided by the marginal distribution of y. So that is what typically gives you, right? If you see here, f of xy is the value of the joint probability distribution of x and y at x comma y, and h of y is the marginal distribution of y at y. The same logic, if you are going with discrete random variables, I can find out f of x given y is nothing but f of x comma y divided by h of y, and and if you are talking of with respect to x, w of y given x, again f of x comma y divided by g of x, where g of x is the marginal distribution associated with x. So we can use the same tablets example that we have used, finding out conditional distribution of x given y equal to 1. So again, just reiterating the values, x is and the x is the set of capsules associated with aspirin, and y is with respect to sedatives, right? So we got the numbers 6 by 36 here, then we had 8 by 36 and 1 by 36. Here we had 12 by 36, 6 by 36, 0, 3 by 36, 0, 0. So this was the probability, joint probability distribution. So what we are asking is, find the conditional distribution given y equal to 1. It's already given, now the y is 1. So this is the 1. When y is 1, these are the possibilities. Now from there I am trying to find the distribution of x. So x equal to 0 given y equal to 1 is nothing but 8 by 36 divided by 8 plus 6, 14 by 36, which will become 4 by 7. So the probability of x equal to 0 given y equal to 1 is 4 by 7. Probability of x equal to 1 given y equal to 1 is 6 by 36 divided by 14 by 36, which is 3 by 7. Probability of x equal to 2 given y equal to 1 is 0. So that's how we are finding out the conditional distribution of x given y equal to a specific value. The same logic I can extend it to the continuous case also. The conditional density of x given y, f of x comma y divided by h of y. Alright, so I can very well use the previous example, wherein I have taken 2 by 3 times x plus 2y, right? That is f of x plus f of x y, which I have used in the previous slide, this one. I will try to find out the conditional distribution of x given y equal to y, right? So let me just take that. So I have f of x comma y as 2 by 3 times x plus 2y, where x is between 0 and 1 and y is also between 0 and 1, and it is 0 otherwise. Now from here we have actually find out, so this is f of x comma y, and I am supposed to find out given y equal to y. So for given y equal to y, so I have to find out h of y. So if I have to find out h of y, I have to integrate this over all the values of x. So I will take it as 2 by 3 times x plus 2y dy. I am integrating across x, so dx. So 2 by 3 times x is x squared by 2, which is 1 by 2, and 2y into x1 So which is the same. So this is what comes out: 2 by 3 into 1 by 2 plus 2 by 3 into 2y, which will make it 1 by 3 plus 4 by 3y, right? 1 by 3 plus 4 by 3y, or 1 by 3 times 1 plus 4y. This is my marginal function, marginal distribution associated with y. So f of xy. So if I want to find out the probability of, or f of x given y, I am taking as f of x comma y, which is 2 by 3 times x plus 2y, divided by h of y, which is 1 by 3 times 1 plus 4y. So this is what is the conditional distribution. So it becomes 2 into x plus y, x plus 2y, divided by 1 plus 4y. So this is what will be the conditional distribution of x given y equal to y. Now I am using it to evaluate probability of x less than or equal to 2 given y equal to less than or equal to half given y equal to half. So I am trying to find out f of x given y is equal to 1 by 2. So this is what I'll get: 2x plus 4y, 4 into half, which is 2, divided by 1 plus 4 into half, 2, 3. So 2x plus 2 by 3 will be the probability of x, will be the probability of x equal to x given y equal to 1 by 2. So this is what we are getting, a function of x equal to x. Now I have to see what is the probability that it is less than 1 or equal to 1 by 2. So I can integrate this from 0 to 1 by 2, the 2x plus 2 by 3 dx. So the first part, 2x by 3. So 2 by 3 into x squared by 2. X squared by 2 is 1 by 2 into half squared, which is 1 by 8. And 2 by 3 into x, which is half. So from this I am getting 1 by 12 plus 1 by 3, which is working out as 5 by 12. So the probability that x is less than or equal to half given y equal to half through this example is working out to 5 by 12. So that's how we can solve these kind of numericals. Then, given the joint probability density, find the marginal densities. So I am getting f of xy equal to 4xy. I have to find out the marginal densities of x and y, and the conditional density of x given y equal to y. So all the things, a quick practice of all these features. So I am setting f of x comma y is equal to 4xy, where x is between 0 and 1, y is also between 0 and 1. So I want to find out marginal distribution, marginal density of x, g of x. So the marginal density of x means I have to integrate across all y. So I am integrate 0 to 1 4xy dy. So which will work out as 4x times y squared by 2, which is 1 by 2, which will give me 2x. 2x is the marginal density of x. Similarly, I can find out the marginal density of y, where I am integrating across all the x. So I am integrating across 0 to 1, integrating across all the x, 4xy dx, which will give me 4y, and integral of x is x squared by 2, again 1 by 2, so which is 2y. So this is the density function of, marginal density of y. Then I have to find out f of x given y equal to y, which is f of x comma y, which is 4xy, divided by h of y, which is 2y, which is equal to 2x, which is g of x. So you could see in this case that the conditional distribution, conditional density of x given y is same as the marginal density function of x, which is what is leading to x and y being independent, right? The conditional distribution of x given y is same as the marginal density of x. So the occurrence of y or non-occurrence of y has not impacted or influenced the probability of x. So this is where we could make out these kind of random variables to be more and more independent. So these events are independent here because we have checked that the conditional distribution, right, the conditional probability does not depend on the occurrence of the event A, then we said A and B are independent. The same logic here, the conditional distribution function of x given y is coming out same as the marginal density of x, then I can very well say x and y are very much independent. So if f of x1, x2, xn is the value of the joint probability distribution function, and fi of xi is the value of the marginal distribution of xi at xi, then if they are independent, you should find that this whatever you are getting as the conditional joint probability distribution coming out as the individual multiplication of the independent probability, the marginal distribution. So if you see here, 4xy was the joint probability distribution, 2x was the density function, marginal density function of y, 2y was the marginal density, 2x was the marginal density function of x, and 2y was the marginal density function of y. So if I am multiplying these two, the marginal densities, if I am multiplying, it is coming out to be same as the joint probability distribution of x and y. So in that case, I can very well say that these events are independent. So I can use their marginal density in case of discrete. I am taking their joint probability distribution and their marginal probability distributions. If the product of each of the individual marginal probability distributions is same as the joint probability distribution, then I can say that the events are independent. Whereas in case of continuous, I can very well take the same statement by substituting density instead of distribution. If the joint probability density of different events is same as the product of marginal probability density function of each of those events separately, then we are still considering the events to be independent. So you could clearly see, if you are considering independent flips of a balanced coin, xi be the number of heads 0 or 1 obtained on the ith flip for I equal to 1 to n. Find the joint probability distribution of these n random variables. So whatever is, if you are talking of xi getting the first flip, getting a number of heads obtained in the ith flip, so either 0 heads or 1 head, because I am flipping it once, I am getting it as a 0 head or a 1 head. So if I can look at getting a head, so fi of xi in this case is 1 by 2 always. So getting a head or getting a tail, and because they are all independent, I will get 1 by 2 into 1 by 2 into 1 by 2 so on n times, which will work out to 1 by 2 to the power n if I am talking of n different flips of a coin. Similarly, you could see here, given the independent random variables x1, x2, x3 with the probability densities given below, Okay, I did not put up the probability densities here. I was looking at f1 of x1 to be e power minus x1, where x1 is greater than 0 and 0 otherwise. f2 of x2 is 2e power minus x2, where x2 is greater than 0 and 0 otherwise. f3 of x3, I am taking it as 3e power minus x3, where x3 is greater than 0. I want to find out what is the probability that x1 plus x2 is less than or equal to 1, comma x3 is greater than 1. So this is where I want to test again whether the independence is existing or not. So let me just quickly look at. So anyhow, it was given in the problem that they are all independent, right? Given the independent random variables x1, x2, x3. So because they are independent, I can very well consider f of x1 comma x2 I can very well consider f of x1 comma x2 comma x3 is same as f1 of x1 multiplied by f2 of x2 multiplied by f3 of x3. So which means I could very well take e to the power of minus x1 into 2 e to the power of minus x2 into 3 e to the power of minus x3, working out to 6 e to the power of minus of x1 plus x2 plus x3, where x1, x2, x3 are greater than 0, otherwise it is. So now I could very well take probability of x1 plus x2 less than or equal to 1 and x3 greater than 1. So how do I take? Let me take first for x1. x1 is lying between 0 and 1. So because x1 plus x2 is less than or equal to 1, x2 will be lying between 0 and 1 minus x1. Right, I can take x2 lying between, because x2 is less than or equal to 1 minus x1. So that's where I am taking it as 0 to 1 minus x1. x3 is greater than 1, so I'll take it as 1 to infinite. And I would like to evaluate this function. 6 e to the power of minus x1 into e to the power of minus x2 into e to the power of okay, I give 2x2 3x3, right? So now let dx1 dx2 dx3. So let's evaluate one by one. Let me do it with respect to Let me evaluate with respect to x2 first, so that I'll finish this off. Everything comes in terms of x1. So let me evaluate in terms of x2 first. So it becomes 6. So it will be 0 to 1, 1 to infinite, 6 e power minus x1, e power minus 3x3, and e power minus 2x2 divided by minus 2. And this would be integrated between 1 minus x1 and 0. So this is where it works out to minus 3 e power minus x1 minus 3x3, and this becomes e to the power of minus 2 times 1 minus x1 minus e to the power of 0, right? So it works out to this much. Now I have minus 3 e to the power of minus x1 e to the power of minus 3x3 into e to the power of minus 2 e to the power of minus 3x3 e to the power of minus 2 into e to the power of 2x1, and here I have plus 3 e to the power of minus x1 e to the power of minus 3x3. So this is what we have. So overall it is working out to e to the power of minus x1 and it is e to the power of 2x1. So it is working out to minus 3 e to the power of x1 e to the power of minus 3x3 e to the power of minus 2 plus 3 e to the power of minus x1 e to the power of minus 3x3. Now the same thing I'll integrate between, now this has to be integrated between 0 and 1 and 1 to infinite. So let me integrate it with respect to the infinite, which is x3. So I'll take it as minus 3 e power minus 2 e to the power of x1 and e to the power of minus 3x3 divided by minus 3. This I am integrating it between infinity and 1. Then I also have 3 e to the power of minus x1 e to the power of minus 3x3 divided by minus 3 integrated between infinity and 1. So this minus 3 is going off here. So I am getting e to the power of minus 2 e to the power of x1. This is e to the power of minus infinity 0 minus e to the power of minus 3 plus this is minus e to the power of minus x1 e to the power of minus infinity is 0 minus e to the power of 1. So it is coming out as e to the power of minus 1. So I think in case of x2s we had a 2. Okay, let me take this. So e to the power of minus x1 into e to the power of minus, right, infinity we have taken minus infinity, so it is minus 3 e to the power of minus x1 into e to the power of minus 3. So overall I am getting as e to the power of minus 2 e to the power of minus 3 e to the power of x1 minus e to the power of minus x1 times e to the power of minus 3. So I could very well take out. Now I'll integrate it between 0 and 1. So which would be like e to the power of minus 5 e to the power of x1. I'm integrating it between 1 and 0 minus e to the power of minus 3 times e to the power of minus x1. So minus will become a plus and this would be integrated again between 1 and 0. So it's coming out as e to the power of minus 5 into e minus 1 plus e to the power of minus 3 times e to the power of minus 1 minus 1. Now when I am doing this simplification, it's working out to e to the power of minus 4 minus e to the power of minus 5 then again plus e to the power of minus 4 minus e to the power of minus 3. So based on this I can very well make out. So if I take e to the power of minus 3 out, it is nothing but e to the power of minus 1 2e to the power of minus 1 minus e to the power of minus 2 plus 1. So this is the typical thing that is coming out. So I can very well simplify it and give the resulting answer accordingly. So that's how I can very well make out what is the probability of x1 plus x2 less than or equal to 1, x2, x3 is greater than 1. So it's just a matter of playing around with the integration part, simplifying the integration part to arrive at the necessary answer. So that's where we have looked at this particular chapter in full. So we have focused on random variables, looked at probability distribution, then for a discrete, and after that we understood what are the continuous random variables. For the continuous random variables we focused on computing the probability density functions. So all this was for univariate random variables. Then we moved on to two variable scenarios, bivariate distributions, then into the multivariate distributions extending the bivariate case. Also looked at the marginal distributions, conditional distributions, and from there even working out with the independent events as well. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.